for the NMR spectrum, we can extract quite a little bit of information. Like you can see that first the number of signals tell you how many distinct type protons you have in the sample. Then the area of each signal tells us how many protons that signal corresponds to. Then the obviously the chemical shift value of each signal will tell you the hint about the environment of each proton. The last thing is splitting of a signal tells the number of types of protons near those correspond to the signal. So this is what we learned from proton NMR. Okay. So what kind of information we can extract from carbon 13 NMR? So the first thing is can we extract the more information from a carbon 13 NMR spectrum in terms of from the intensity of individual peaks. Unfortunately, in this case, the peak area doesn't really tell us anything about the number of carbons. This can be easily illustrated if we look at NMR spectrum of this compound. It's basically called metacresol. Okay, basically the methyl-phenol. And the exact, the assignment of every carbon, we can talk about that later. Okay? But first thing is, what you can see, this compound has how many carbons if you look at it? Count, how many carbons this compound? Has a total, benzene has 6, okay? Then one methyl group, so they have 7 carbons. And all these 7 carbons, they are unique. So you actually can see 7 peaks. 7, the carbon 13 peaks, 7 of them, okay? So you know that every carbon, you have one of them. Every carbon you have one of them. But you see the peak area, the peak intensity, they're quite different, okay? So that immediately tell you that, using this one example, the intensity of carbon 13 NMR peak does not mean anything, okay? So if you really go to details of how carbon 13 NMR spectra are collected, you can gain some more information about the intensity, but it's not related to the number of carbons produced as the signal. Because as we know, we know every signal corresponds to one carbon, but the intensity is different. Okay, so you basically know the intensity at this point. What you can say the intensity of a carbon 13 NMR, the peak does not tell you anything. That's just an easier way to say it. Okay? Why that's the case? That's related to how carbon 13 NMR spectra are collected. Because carbon is a lot more less sensitive than protons. So the spectroscopists they basically invent a method to enhance the signal of carbon 13 NMR, and those enhancements distort the peak intensity and number of nuclei coloration. So it's not really basically just forget about the peak intensity in carbon 13 NMR. And also, if you notice, every carbon signal you see here always is singular. Okay. Again, this is related to how carbon 13 NMR spectrum, how they are collected. Okay? Because of the way, the special way they were collected, so all spin splitting are eliminated. So basically, you also don't have any spin splitting information. So only information pretty much you can see from carbon 13 NMR is how many different types of carbons and the chemical shift value of the carbon can give you a hint about the local environment of the carbon. I hope you can see that all 7 carbons are different. Okay, how do I know every carbon is different? Okay, you can look at some special carbon in this compound. Like the methyl carbon is special, unique, okay? Because all other carbons are aromatic carbons. So only this carbon is not aromatic carbon. So this is a special carbon. So immediately we know this carbon gives you signal here, okay? Because all aromatic carbons should be around 120 ppm or slightly higher. Okay? So this is a unique carbon. Okay? And then next unique carbon is a ring carbon connect to oxygen. Because all other ring carbons, they are either connect to hydrogen or carbon. They don't connect to the oxygen. So this ring carbon connect to oxygen. So this one is unique. And this one give you the peak at close to 160 ppm because oxygen is the most electron withdrawing group here. So we're going to deshield the carbon direct connect to. Okay. Then this carbon also different from this carbon, although both are ring carbons. Okay. But this ring carbon connect to the other ring carbon connect to methyl group, and the other end connect to the carbon connect oxygen. So this carbon is different from this carbon. Okay. Because this carbon we know one end connect to a ring carbon with a methyl group, the other end just connect to regular ring carbon atom. Okay. For the same reason, this carbon also different from this one. Okay. And this carbon different from this one. That's why you have all 7 different carbons. Okay. Under the in many cases, if you want to know how many carbons, how many different kind of carbons you have, in uh, in a molecule, you can utilize the symmetry argument. Here. Symmetry argument. So just give you some examples. Okay? If you look at so how many carbon 13 NMR peaks you are expecting from this compound? So you can draw a line, separate the molecule into two, the symmetry related parts. Okay. So the top and the bottom part, they are symmetrically related. So this basically that leave this molecule only has like 1 carbon, 2 carbon, totally 3 carbons. Okay. And those 3 carbons, if you look at the chemical shift value, this carbon should have the highest chemical shift value. Okay. Then this is the second highest. This carbon is at the lowest chemical shift value because the oxygen atom is the electron withdrawing group here. Okay? So this carbon is deshielded to the largest degree by this oxygen. Then those 2 carbons, okay, they are one more bond away from this carbon. So they are deshielded to a less degree. And those 2 carbons, they are deshielded to the lowest degree. So the another example, if you look at this molecule, how many carbons, how many types of, the carbon atoms you have in this molecule? Look, this molecule obviously have, the 3-fold symmetry. Okay, so the molecule you can imagine at the center of the molecule have 3-fold rotation axis. So you can cut this molecule in 1/3, and you can rotate around the axis can reproduce the entire molecule. this molecule has a threefold, the symmetry axis in the center of the molecule. Okay? So if you look at that, then so if we cut in the, one third, so the unique carbon, we have, this is one unique carbon, this another unique carbon, and this is third unique carbon. Because it has a threefold rotation axis, so you only have like the 3 unique carbons. And now if you look at this molecule, how many unique carbons do you have? What kind of symmetry element it has? Two-fold symmetry, three-fold symmetry, or four-fold symmetry, or six-fold symmetry? Be observant. What kind of symmetry this molecule does it have? Yeah, two-fold. Okay. Basically, you can have a mirror plane going through middle of molecule, top and half that mirror each other. Okay? So that's like in this case, you just count a half. Basically, the top half will be sufficient. 1, 2, 3, 4, 5. Okay, you have 5 different carbons, 5 unique carbons. So this is just something when you think about, how many, the carbon atom, and therefore how many carbon 13 NMR signals you can expect from a compound. This molecule, how many types of carbon atom do you expect? How many types of carbons? Huh? Or, as well as some said, counting is hard. Of course, we'll slowly count. Okay, so make sure I don't make a mistake. Just we count it. Okay, so we know that that's have a two-fold symmetry there. Okay, then just count just take a part of the just a unit of the symmetry element. Count the 1, 2, and 3. Did I miss any carbon atoms? We only look at carbon. Oxygen is not part of the equation. Carbon, okay? So it's only 3 carbons. So come careful, okay? So the same thing for proton and mass. So this symmetry argument apply for both carbon and proton. But just say in case of proton, if you are in doubt, you're always can use called replacement test to generate the 2 compounds. Okay, and you see whether the 2 compounds are the same or not. Whether the 2 protons are equivalent or not. But carbon 13 is a little bit trickier because it's hard to replace the carbon with something. You can try to replace carbon with silicon. Then see whether if you are questioning whether 2 carbons are same chemical equivalent or not, you can try to replace the carbon with silicon, see whether the compounds are the same. But often the symmetry argument, is very useful. Okay. So what we can say is that from carbon 13 NMR, if you look at carbon NMR 13 NMR spectrum, you only see how many types of the protons you have, how many types of carbons you have in a molecule, and the chemical shift value of each carbon. I will tell you, give you a hint about the environment of the carbon. So if you want to know, if you want to decode the local environment of carbon from its chemical shift value, you can make use of this table. Okay? This table will be provided if you're asked to decode carbon 13 NMR. So you don't need to memorize it. Now that's basically end of the NMR. So we know that overall in a spectroscopic method, we always send in a beam of wave, electromagnetic wave. Then generally we look at the absorption spectrum. Then we try to figure out the what kind of sample we have there. Okay. So in case of NMR, we use a radio frequency wave as an electromagnetic wave to interact with our sample. But we also can, in other spectroscopic methods, we can also use different, the electromagnetic wave. For instance, in infrared spectroscopy, we're going to use infrared beam to interact with our sample. Then we generally look at the absorption spectrum, then try to figure out, the information about our sample. And in the UV visible spectroscopy, we're going to use, we send a beam of the UV or visible light going through our sample. We're also going to see the absorption spectrum and figure out information about our samples. So I hope you know that when we're sending radio frequency wave into our sample, some of the photons will be absorbed because of that transition between two nuclear magnetic energy states. Okay? Now, if we are sending infrared waves through our sample, and if some infrared photons are absorbed, that is because there are energy levels. Okay, there are different energy levels due to the vibration of molecules. So when we say vibration, you probably can imagine just, let's say, anything can vibrate. Say like, I don't know, if this oil vibrates, you can see it vibrates, okay? So but this kind of vibration is more like a bending, you see it vibrates, but it's more like a bending, okay? But if you have a real spring, you pull it, okay? Just you stretch it and release, you're gonna will vibrate like this, okay? So this kind of vibration is called stretching vibration, and just as the name suggests, it becomes longer and shorter, this kind of vibration. So the stretch vibration is a kind of vibration we will consider the most, in this chapter. Okay, so if we look at a molecule, the stretching vibration basically refers to those vibrations that change bond length without change bond angle. Like here we can see the CH2s. So the black one is a carbon. This carbon, those are two hydrogens. So we have the two CH bonds connect to the same carbon. So this vibration basically shows that the two CH bonds, the length simultaneously increase and the decrease. So just like if this is like this, okay, this kind of vibration, this is called symmetric stretching. Means the two CH bonds simultaneously increase or decrease the length. This is called symmetric stretching. Okay? And the other kind of stretching vibration for the same CH2, you also can have like this. One becomes longer, the other becomes shorter. This is called, the anti-symmetric stretching. One becomes longer, like this one, like this called anti-symmetric stretching. Okay? So the all the CH2s or CH3s, they have that kind of symmetric anti-symmetric stretching, but we don't need to worry about too much. Just this, there's a stretching vibration exists. Okay. The other kind of bending vibration mode is that the bond length don't really change, but they change bond angle. It's called bending. Okay. Exactly bending the type of bending vibration, I'm not going into details. Just just for your information. Let's assume my two arms, they are CH2s, okay? This kind of called scissoring motion, okay? They basically come back and forth, scissoring motion, okay? And the what called this kind of motion called rocking, simultaneously move, called rocking, okay? And this kind of called wagging, okay? Simultaneously going up and down called wagging, and this called twisting, okay? This all bending motion. I'm not gonna test you, but just give you a sense. Okay? So scissoring, as the name suggests, okay? Rocking, simultaneously going up and down. This is called rocking, and rocking this way, sideways. Sideways, this is called rocking, and the wagging is simultaneously up and down. The twisting is one up, one down. This is called four kind of bending motions. Okay? But as I said, we're gonna focus on stretching. Because stretching vibration, like just one to become, let's say, longer than this. Assume this two bonding atoms become longer than shorter. Okay, that's easy. Can be relatively easily, treated mathematically. Okay? So the infrared spectroscopy basically involve, as the name suggests, involves the application of infrared light to sample with observation of the IR light absorbed, mostly absorbed. Okay? And the infrared spectroscopy is not as informative as NMR spectra in general. Basically, NMR spectra, if you remember the examples of the four examples I gave for the alcohol, they actually could be very, very informative. Okay? In terms of help you find out what exactly kind of compound you have. But infrared, the spectroscopy, the generally can tell us whether we have a certain kind of bonds as a functional group, and could be, the very sensitive to those highly polar functional groups. Why that's the case? Because this is important. Okay, take note. Okay? So the how strong a particular vibration can absorb infrared, the ability of a vibration to absorb infrared photons directly relate to the change in dipole moment, the resulting from a particular vibration. Okay, so if during a vibration you have greater change of dipole moment, then that vibration gonna have a strong ability to absorb infrared photons. Let's take. I'll give you some examples. Okay. Now, for instance, if you look at a CO double bond, okay, let's look at this bond alone. Okay. This bond is one of the most polar bonds you have. It's not the most polar, but one of the most polar bonds you have. That means in this bond, carbon carries a great amount of positive charge. Oxygen carries a great amount of negative charge because oxygen is a lot of more negative than carbon. So this one is very polar. So when this bond stretching, okay, means become longer, okay, or become shorter. The dipole moment change a lot because here the positive charge, here negative charge. And dipole moment of a bond is the amount of separate charges times the distance. Over the distance they are separate. Okay? So if this one is a highly polar, then you stretch it, the dipole moment will change a lot. So that's why this kind of highly polar function group, it can absorb. Very good at absorb infrared photons. Okay. For the same reason, if you look at OH group, okay, the OH bond is even more polar than, not necessarily even more polar, but it's also a very polar bond. So this bond why it's stretching vibration. It's very, very good at absorbing infrared photons. Okay. Now, if you compare OH and the CH, okay, and the CH bond is substantially less polar than OH bond. So stretching vibration of CH bond is not that good at absorbing infrared photons. So although you have a one OH bond with let's say 10 CH bond, probably you're going to see a bigger peak from the OH bond stretching vibration compared to the 10 CH bond, okay? Because OH bond is not polar than CH bond. Similar reason, if you look at say COO, okay, the CC double bond. CC double bond itself is not polar, okay? So whether the particular CC double bond is polar or not depends on the local environment of two double bonded carbons. In this case, the two double bonded carbons, they are exactly same. Exactly same. So this CC double bond will be completely non-polar. So you will not be able to see the infrared absorption peak of this CC double bond stretching. Okay, you will not be able to see that. Okay, and on the other hand, if you have say this molecule, now what's the difference between this the right side one and the left side one? The right side molecule, you know, you have the CF3 as an electron withdrawing group, okay, and the CH3 is the electron donating group. So you see that this CC double bond is substantially more polar than the left side CC double bond because the electronic effects of the substitute with the two double bonds. So this one will be positive charge, okay, carbon. This one will be negative charge. So this CC double bond becomes polar, and it could give you substantial, you know, it has a sizable ability to absorb infrared photons just because of the CC double bond stretching, you know, it will absorb infrared photons because this CC double bond is actually polar. And if you have this molecule, so this molecule, the CC double bond stretching vibration, probably will give you strongest infrared absorption peak because, you know, the CC double bond is the most polar out of the three CC double bond you see here. Okay. So that's you know the one difference about the infrared and the proton number. Proton number you see is basically just a constant number of protons will directly proportional to the peak area. But in infrared, you really have to pay attention to the dipole moment, okay, of the, you know, the functional group you're looking at. Okay. So this is so infrared spectroscope is very sensitive to those highly polar functional groups like OH group, like carbonyl group, and the CO bond. Those are, you know, basically look at the polar stuff. Non-polar stuff is not very sensitive. Okay. And then in terms of how does the infrared spectrum look like, you probably have seen in organic lab already. Okay. So in the infrared spectrum generally represent, you know, is given in the form of you know, absorption or transmission. Transmission is just, you know, as the name suggests, how much light goes through. Okay, this is called transmission. Or you can, you know, in the spectrum also can be given in the form of absorption. If the absorption, it will be similar with NMR, the peak go upward. If the transmission, the peak going downward. Okay, so here we are giving the infrared spectrum in the transmission form. So the bigger the downward peak is, the means you have stronger absorption. And the the x-axis is but the frequency in infrared, due to historical reasons, is given in a unit called reciprocal centimeter. So but it is a frequency unit. So what is the meaning of reciprocal centimeter is basically you 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 find that the wavelength of infrared, the photon, then convert into centimeter, then calculate the reciprocal of the wavelength, then give you a number called wave number in the unit of reciprocal centimeter. So like here, let's say if look at this guy, the two 2500 reciprocal centimeter. What does that mean? That means the infrared photon wavelength equal to 4 micrometer. Okay, 4 micrometer, is 4 times 10 to minus 6 meter, right? That's equal to 4 times 10 to minus 4 centimeter. Okay, so there you calculate the reciprocal of this one. And equals 2500 reciprocal centimeter. Okay, so that's how the wave numbers come from. But it's a frequency unit. You don't have to do this calculation. I'm not required to do this calculation, but just keep in mind reciprocal centimeter is a reciprocal wavelength unit, and the reciprocal wavelength unit is directly proportional to frequency. That's sufficient for you to know. So just like a frequency, wave number is directly proportional to energy. So if you look at infrared spectrum, generally you can split the infrared spectrum into several regions. So the higher frequency region in general is start from about 4,000 reciprocal centimeter to about 1,500 reciprocal centimeter. And this region usually, come from the stretching vibrations of those functional groups. So this region, okay, also called a functional group region. So the kind of infrared photons usually used for the spectroscopy analysis start from about 4,000 reciprocal centimeter and end up around 500 reciprocal centimeter. So those kind of photons we call mid-infrared photons. So this is the most commonly used, the type of infrared photon. So usually we for high frequency end we start around 4,000 to about 1,500. This called functional, group regions. Okay, and those the low energy vibrations smaller than 1,500 reciprocal centimeter, and they are usually not super useful, and they could vary greatly for different compounds. So we actually can using using this region to identify individual compounds. And obviously that requires great deal of memorization. So I'm not require you to memorize the fingerprint region. I'm not require you. So even myself, I cannot read out, with a few exceptions. I probably can remember a few compounds in fingerprint region, and nothing beyond that. But we don't have to memorize a lot because we have those commercial valuable software packages. You can have all the data stored in a database. So if you want to check what your compound is, just you have your infrared spectrum to match the spectra stored in the database. If you find a match, it will tell you all your compound is what. So you don't need to do a lot of memorization. But I do require you to acquire the ability to use a functional group region to identify, what kind of functional groups you might have or you don't have in the compound, if based on its infrared spectrum. Look at some examples, okay? So this is infrared spectrum of hexane. So hexane, only functional group you have is sp3ch, and the carbon-carbon generally is not polar, so you don't really see absorption of the carbon-carbon bond in infrared. At least it's not. It's quite difficult. Let's put this way. Now, and the sp3ch bonds, I do ask you to remember, okay? sp3ch bonds, in general, they give you, its stretching vibration give you a few peaks, always slightly below 3,000 reciprocal centimeters. This I do ask you to memorize, okay? sp3ch, their stretching vibration give you the infrared absorption, a few infrared absorption peaks, slightly below 3,000 reciprocal centimeters. It's not that hard to remember. Slightly below 3,000 reciprocal centimeters. Okay? Now, if you look at this guy, it's a hexene. Means if you look at functional groups, you have CC double bond, you have the vinyl CH bond, means the CH bond connect to sp2 hybridized carbon. So this is sp2 hybridized carbon. Okay. So this is sp2 hybridized carbon. You have the CH bound to sp2 hybridized carbon and the CH bound to the sp3 hybridized carbon. So we already know that the sp3 hybridized CH going to give you a few peaks slightly below 3,000 reciprocal centimeters. Okay, those are sp3 hybridized CH. But also you have the weaker peak, slightly above 3,000 reciprocal centimeters. This is sp2ch. And we will further look at the relationship of the vibration and the hybridization of the atom. And the CC double bond generally give you absorption around 1650 reciprocal centimeter. But because the polarity is generally low, so the peak here is actually weak. But this CC double bond is it's not completely non-polar, because one end you have if you look at two CC double bond, look at this CC double bond. At one end you have LQ groups attached to it. The other end there's no LQ group. So that makes this CC double bond somewhat polar, so you still can see it. Benzene, only kind of CH bond you will be seeing is sp2ch. So that's why you see only CH stretching peak is all slightly above 3,000 reciprocal centimeters. You don't have any sp3ch. So these are some examples. Okay. Now, if you have alcohol, this one is what's the name? How many carbons? We have 6 carbons. Hexanol, one hexanol. Okay. One hexanol has one OH bond, and how many CH bonds here? 8, 11, 13, right? You have 13 CH bonds and 1 OH bond. Okay? But if you look at so this peak OH bond come from OH stretching vibration. If you look at peak area, is actually larger than the 13 sp3ch. See, this peak is slightly below 3,000 reciprocal centimeters. So those peaks, they can be attributed to the sp3ch stretching vibration. And this single intense and broad peak come from the OH group stretching vibration. Okay? So if you look at peak area, you probably can see this peak area is actually larger than this. One OH group, okay, one OH bond, okay, has a bigger peak than 13 CH bond. Why? Because the OH bond is a lot more polar than CH bonds. So that means a single OH bond, its stretching vibration has a stronger ability to absorb infrared photon than 13 CH bonds. Because OH bonds are a lot more polar. And why the peak is so broad? Can anyone guess why OH peak is so broad? And anyone recall that in the proton and the MAR, when we say OH peak, the chemical value can vary a lot. Anyone recall that? OH peak, the chemical shift value can vary a lot. And why OH peak chemical shift value can vary a lot? CH usually don't vary much, okay? But OH peak can vary a lot. And for a given compound, can vary a lot. Depend on concentration, depend on your environment. But if it's CH, if compound is given, chemical shift value usually don't change much. Okay? But why OH chemical shift value can change a lot? Anyone can recall? Proton and MAR, OH chemical shift value can change a lot. Let me see. Rosa, Amanda Rosa. Not here. Okay. Then let me see. Madison Lee. So do you recall why OH chemical shift value could vary a lot?
Because it's a hydrogen bond.
Yes, OH, very good. Okay, OH group, just like NH group, OH group even has a better ability to engage in hydrogen bond. Okay? So but the hydrogen bond is an intermolecular interaction. Okay, so it's not exactly, it varies with a lot of things. Means that concentration is most important, and the solvent. Okay, so they can vary a lot. So for some reason, this OH group, okay, they also can participate in hydrogen bond. So when they participate in hydrogen bond, the peak broadens because you have different kind of OH groups. Some of them may participate in hydrogen bond better than the others. Okay, that's why it's why it become broader. Okay, but anyway, this is one feature. If you have an OH group in the molecule, you will never miss it. It should give you an intense peak, infrared peak, and generally broad. This actually going to be very useful when you do your unknown in organic lab. Okay? If you have OH group, you should never miss it. Okay? It should be intense peak and generally a broad peak. And the nitriles is a class of compound that has the CN triple bond. And the CN triple bond actually give you a medium intensity peak, generally sharp, around 2200 reciprocal centimeter. Okay? And here again is the sp3ch. So if you see a few peaks slightly below 3000 reciprocal centimeter, those always are sp3ch. And the carbonyl group is the star functional group of organic food. And again, you see this one, this compound has how many CH bonds here, sp3ch bonds here? 12, okay? And the 12 sp3ch bond give you this, this a few peaks. at slightly below 3,000 reciprocal centimeter. And the CO double bond give you intense and not that broad peak at around 1,700 reciprocal centimeter. This is a signature feature for the CN double bond. So if you don't see a peak in the neighborhood of 1,700 reciprocal centimeter, you can rule out the CO double bond. If you do see a peak at around 1,700 reciprocal centimeter, then you have a CO double bond. So this is also going to be extremely important when if you're going to do your unknowns. Okay? CO double bond, you will never miss it. Again, it's intense, it's not broad, intense and sharp. In the infrared. Why? Because CO double bonds are very polar functional group. So the NH bonds, its absorption, its ability to absorb infrared is substantially weaker than OH. You see here how many? Again, let me count the CHs. This 13 CHs and the 2 NHs. And these two the absorption peak of the NH absorption peaks, they are much weaker than OH. Although you have 2 NH bonds and you only have 1 OH bond here, okay? But you see the 2 NH bonds produce a weaker absorption peak than 1 OH bond because N, after all, is substantially less electronegative than O. So the NH bonds are much less polar than OH bonds. NH bonds only somewhat more polar than the CH bonds, yes, but substantially less polar than the OH bond. That's why the absorption peak is much weaker. So here at the table, basically tell you, what are the possible, the functional groups if you have the absorption peak in certain range. Okay, so I'm not gonna ask you memorize the entire, the table, but I'm gonna ask you to memorize those things. Okay, and we'll give you some quantitative explanation.